Hi, so I'm Andrew. I'm with Certora. I've been working on verifying some of Euler's code, including the EVC and Vault kit. And today I'm going to tell you about verifying the Euler Vault with the Certora prover. So this talk is split into two parts. The first part, I'm going to give an overview of the Certora prover, how to use it, what it's doing under the hood to help you use it in the contest, and also go over some of the setup specific to the Euler Vault. So when we do formal verification, we take two things as input. One is the implementation source code, and then the other is a formal specification of properties that we expect it to have under all situations. And we either get as an output a proof that it really does have all of these behaviors under all possible inputs in all the reachable states, or we find some rare behavior where this property actually doesn't hold, and maybe this is either a critical security vulnerability or some other bug. Specifically with the Certora prover, the way we do this is we compile both the specification and the Solidity code into a logic, and then we use an SMT solver to either give us this formal proof or this counterexample that can help you find the vulnerability. So let's see how this works for a simple contract example that's just implementing a bank. The bank just holds a collection of funds for the user addresses, and it has two functions. One is a deposit function that just lets the caller deposit some funds, and the other is an accessor that lets you check how much funds a given address has. But how do we know that this bank really implements what we expect? In this case, it's probably pretty clear to see that it does work, but how do we check that this deposit function really does just store the amount that the caller intended to deposit? So let's see how to do that with a specification in CVL, which is the Certora specification language. This rule deposit OK does exactly this. It takes an arbitrary uint256 as an amount. And then on the following line, we have this environment variable, which is a special type in the Certora prover, which lets you reference the global variables in Solidity, such as the block timestamp or the message sender address. On the following line, we simply save the funds that the caller had before calling deposit. Then we call the deposit where under the hood, the tool is going to inline the source code from Solidity so that we can check facts about the source code. And then after that, we simply save the funds that the same user had after calling deposit. And finally, we write this assertion that lets us check that the amount that the user had after calling deposit is really just the amount before plus whatever amount they deposited. And importantly, if we're able to prove this property, it doesn't just mean we've run a bunch of test cases. We really prove that it holds for all possible inputs and all the reachable states. So now how do you run this? The first thing you need is a configuration file. The configuration file shows the Solidity source code that you want to verify, the specification file that has the rules you want to verify, and then there's some other options like that could let you do performance tuning. If you want to understand what all of the options are, you can simply run Certora run --help. It gives you relatively complete documentation about what is available there. And then once you have your configuration file, you run the tool by simply calling Certora run with the configuration file. Once you do this, it'll actually run your verification job in the cloud, and it'll give you a URL that points to our web UI that has the results of verification, along with some tools that can help you debug further if you need to. So this shows an example of what our web UI looks like. And importantly, on the left-hand side, it'll show you the result of all the rules you run. In this case, we have just one rule, and it passes. So we get a little green check mark that says it's verified, it's proved for all cases. There's also some other helpful stuff here to let you debug in case that's necessary. So let's see what happens when there is a bug, though. And to do this, let's just introduce a really simple bug that just deposits amount plus 1 instead of the intended amount. If you do this with the same rule, instead of verifying, you'll get a counterexample. And in the web UI, this is indicated with a little red X. And then there's some other tools to help you debug the counterexample and understand what's going on. On the right-hand side, you'll see a valuation of the variables. So when you have a counterexample, this means the tool has found a specific valuation for the variables where this property does not hold. And in this case, you can see that the amount, even though the amount that was given to the deposit function and the funds that the user had before the call were both 0, somehow after deposit, the amount is 1. So you can see clearly there's something going wrong. Another useful tool to help you dig into what's going on is the call trace. The call trace is in this pane in the middle here, and it basically gives you a bit more information about what the contract is doing with this particular counterexample that it found. Notably, when there is a counterexample, it's not unique. There might be multiple counterexamples that violate the rule, but this will show you what the contract is doing for this specific counterexample. And in particular, it'll tell you the storage values for each of the function calls as you step through it, the specific parameters that get past all the functions, and branch conditions that do get evaluated on this execution path with the particular counterexample. So this can sometimes help you find what's going on. And indeed, in this case, it shows that get funds does return 0, which we would expect, but that somehow, even though deposit is called with an amount 0, there's a write to the storage location for the funds with 1 instead. So this should hopefully give you a clue that the line where the storage is done is incorrect. So next I'll go into a bit of detail about what's going on under the hood in the prover, because sometimes this might help you understand what it's doing and how to get the most out of it. So importantly, the Certora prover actually works on EVM bytecode. There's two main reasons for this. One is that we can actually support more languages than just Solidity. We can support languages, any of the languages that work on EVM, like Viper. But perhaps even more importantly than that, this lets us reduce our trust assumptions about the Solidity compiler, because we're actually proving properties about its output and not just the source code. And in fact, we've even found some compiler bugs this way. The next step is that we convert the EVM bytecode into our own intermediate representation called TAC, which is based on the classic 3-address code intermediate representation, which simplifies some of the static analyses. The reason why this is useful for you to know is that it's a bit transformed from the original Solidity input, and so sometimes the web UI will show you this more assembly level outputs, and this can help you debug what's going on in some cases. Once we have TAC, we then do some other optimizations. For example, we can do a points to analysis that shows which values different regions of memory can point to, and let us segment the memory into completely disjoint sets and then eliminate some unused code. So for example, if we have a verification condition that checks this structure X, and we have some other structure Y, and the verification condition doesn't have anything to do with Y, we can simply eliminate this extra code, which simplifies the problem that we hand to the solver. So once we have the optimized TAC code and the specification, we can finally convert both of these into logic, which the SMT solver can help us check. Under the hood, the Certora prover works using SMT, and all of the major SMT tools use the same format, which is this SMT-lib format. And this shows an example of how to encode a simple algebra problem in SMT. So imagine you have 3 variables, circle, box, triangle, and then you have these equations that they have to satisfy. The assertions directly encode these equations, and then the line right after the assertions, check set, asks the prover to say, is there some set of values where this does actually hold? Is this satisfiable? And in this case, on the following line, it says get model, which returns one example where this is satisfied. And in fact, yes, this is possible to satisfy if circle is 5, box is 2, and triangle is 1. However, if you imagine we added this extra constraint, which says circle can't be 5, it's no longer satisfiable. And when you get to check set, it'll say, no, this is not satisfiable, and it won't be able to get you this model. So now that we know a little bit about how SMT solving works, we can return to see how we can use this to do program verification. So an oversimplification of how this works is that we basically take the code that you're trying to verify, convert it into these logical formulas. We then take the rule that you're trying to prove about it, convert it into logical formulas, but then we negate the rule. Then this means if it's satisfiable, that means we actually have a proof that it's never violated, because it means we can find no input where the condition is not true. And if it is satisfiable, this means we have a concrete counterexample where the rule is violated. So that's it for the portion that's going over the Certora prover. Next, I'll talk about the setup for Euler in a bit more detail. So the scope for verification is the following modules: borrowing, which handles borrowing and repaying of assets; governance, which allows the governor to configure fees and other properties; liquidation, which handles liquidation of unhealthy accounts; and the risk manager, which handles vault and account status checks. So why is this the scope? The first reason is that the prover runs relatively smoothly on these, and in fact, we already have a setup that should just work out of the box for you. And you'll spend your time writing useful properties. The second is that these both have some potential for risk, and as a result, some value for formal verification. So this is in the context repository, of course, the source directory has the original Vault implementation that you're verifying, and then in the Certora directory, you have the files related to formal verification with our tool. So the conf directory has the configuration files. Harnesses has some other Solidity code that helps do formal verification. Helpers has some mocks that essentially mock the underlying ERC20 asset. And lastly, specs has the specifications for verification. So in the configuration files, we have one for each module, and these have essentially the contracts that the prover is meant to run on and the specification for verification. There's also some performance tuning options, but for the most part, we hope that you'll be able to ignore these. If you want to dig into it a bit more and understand what's going on, you can use Certora run -- help and see what other options we have available. But for the most part, you should be able to just ignore this and directly use the one for the module you're verifying. We also have harnesses, and harnesses help do verification. For the most part, these are used to let you refer to private Solidity functions in CVL rules. And the way this works is essentially it's a contract that extends from the contract you're verifying and just includes a public function that calls the internal one and directly passes the value. And you may need to tweak these a bit to add more harness functions to cover the part that you want to mention in your specification. The spec files have a base setup for each of the modules that are in scope for the contest. The Vault also has a few other examples to help you get started and maybe inspire you to come up with other properties. Another useful thing to know about in the specification directory is base.spec. This is not actually a set of specifications, but instead it's some reusable setup. And it's important to make sure that you keep this imported in all of the specs that you're writing. This also has a few other helper functions. So for example, actual caller is what you're likely going to want to use rather than message sender directly, because generally the Vault is called indirectly through the EVC, and so the real address of interest is more likely going to be the get current on behalf of account from the EVC, which this helps set that up. So here are a few other resources to help you get started. First, we have a collection of nice CVL examples in github.com/Certora examples. Covers a wide range of properties and how to cover a wide range of things in CVL. There's also, of course, the official Certora documentation, as well as our help desk on Discord. Of course, before you get to verifying, you'll also likely want to check out the Euler light paper and Euler Vault Kit white paper.